to this computer. All right, today we're going to start out by reviewing a couple of things from CPS 161 and what these basic ideas are. There's three basic ideas for sorting that we took a look at last semester. And then we're going to look at some bizarre ways with some new data, that's double air quote, data structures that we've learned and how we can do sorting. And we're going to take a look at one today that's called the heap sort. And it's it's an interesting one. Most definitely interesting. It's found in the NIOP book. And yeah, yeah, hopefully I do a okay job explaining it so you know what's going on. So let's go back to the good old days of a selection sort. And a selection sort was one where I make a pass, select a number, and then move it to a spot. So, for example, if I was to sort this in ascending order, A to Z, I kind of would like to start in this first location, search the rest of the way out to find the smallest number, and then swap it with the beginning. Okay. So I'm going to say I need one loop, an outer loop, starts at 0, counter 1 equals 0, counter 1 something, and counter 1 plus plus. Could you come up with some help for me here? I want to start at the first one and then compare it to the rest. Then move to the next one and compare it to the rest, and so on in this idea of selecting a value. So what's my first loop going to be from 0 to
Size -1.
size -1? So less than, so I want to go, if this is 0, this is 10, this is 11. I'd like to go, yeah, see, I need to draw the picture and write it down. So if size is 12, I'd like to go from 0 to just less than size -1. Didn't leave myself enough room. Size -1. Eraser boogie. Counter 1, I want to go from 1 to 10. My inner loop for counter 2, where does it start?
It starts at position 1. Well, it starts at counter 1 plus 1.
Excellent. Counter 1 plus 1. And so far over the three courses you've had, you're starting to see how some of these get manipulated around. And yeah, it's starting to get pretty good at that. And you want to go while counter 2 is, I want to go, yeah, go
Less
ahead.
than size -1.
Will I ever get to that 11th one? Because I'm going to do this first one with the rest, 9 with the rest, 13 with the rest, 1 with the rest, 7 with the rest, so that it would just take a look at those two. So I need that 11th spot. So can I just say less than size? Yeah, good idea. Okay. So right now I'm going to get in and I'm going to use some sort of if notation. And, I need to keep track of where I'm at right now, which I know is counter 1. And then where is the smallest after that? And its location. Like I need this ninth spot. So first thing I'd say is this is the smallest one. This is smaller, so I want to save it. So now I'm thinking 4. If I keep going, oh, 2 is smaller, so I need to save that. If I keep going, 1 is still the smallest. So I'd have to do a whole bunch of things like, while I'm in here, small equals my location, current one, or counter one, small value equals whatever the array is sub counter one. And I would need an if statement to go through the rest of those. Or maybe this has to be moved up, some jockeying around. But the concept of the selection sort is what we just sort of talked about right there. I don't need to go through the code. You should be able to go through the code. You're going to keep going until you find the smallest one. Then you're going to swap. Then you're going to swap it. We had swap. Let's see, void, swap, ampersand, num1, ampersand, num2. Does that look about right? Temp equals num1, num1 equals num2, num2 equals temp. I pass those by way of reference. Yeah. Okay. Selection sort. I'm selecting a value. What's the big O notation on this?
O to the N or ON.
No, it's not going through just one time. N times N. It's going to be N squared. Big O sub N squared. That's that idea of two loops. Because if it's 1,000, we're getting we're getting pretty close to N times N. Okay. Exchange sort. Start to remember some of the exchange sort. Exchange. There were a couple. There was the bubble sort. There was the Dan sort. But I can do one of two things. I can go through side by side and exchange 10 and 4, 10 and 8, 10 and 11 are okay. 11 and 6, swap. 11 and 2, swap. 11 and 9, swap. 11 and 15, okay. 15 and 30, swap. And I could just keep going through, swapping all the way out. And I would end up with, looks like the largest number was working its way out. And then I did something, if there was a swap, do it again. If there was a swap, do it again. That was one of the bubbles, right? I did a side by side. The Dan sort went from, in this case, there's 12 items. This is 0. This is 11. Excuse me, 10. And this is 11. The Dan sort did something along the lines of it compared 0 to 1, 0 to 2, 0 to 3, all the way out to 11. And then it did 1 to 2, all the way out to 11. And then 2 to 3, all the way out to 11. I took this one and compared it to all of them. And that first sort I said got the largest at the end. This sort's going to get the smallest to the beginning first. Again, big O sub N squared. Okay. The first one was more side by side. That was that bubble. And then the Dan one sort of just was a grunt one. The third type of sort, which we really didn't get into very much, was called the insertion sort. The insertion sort. How did the insertion sort work? Well, what happened was I put a number in, 10. That list is sorted. Now I'm going to put another number in, 4. Uh-oh. It's smaller than 10. So now 4 goes in the front and 10 goes in the second. So as I go through, I'm inserting to the spot I want. 8 greater than 4 but less than 10. This becomes 8 and the rest of the list gets moved down. The answer on the test last year was deck of cards. If I'm playing cards and I'm picking them up one at a time, I probably will sort them this way, putting them in order. Yeesh. Just to review: selection, exchange, insert. Now, the brain's probably saying, yep, that's pretty good. Can there possibly be more? Oh, yes, my friend, there is more. Today, we're going to learn about a heap. Oh, boy, a heap. And we're going to take a look at how a heap sort would work. A couple we just looked at were n squared. This heap sort is going to be n log n. Oh, if I was a dummy and I had a review on how to figure this out, I probably would know how. It's a type of selection sort, which means I'm going to be grabbing a value and I'm going to be moving it somewhere. So a minute ago, we were talking about grabbing a value in that first selection sort and moving it to the end right away. Well, we're going to do the same kind of thing. We're going to find the highest and move it to the end. Now, the problem is I need to do a little pre-work, create a heap before I can do the heap sort. All right, here we go. It's another data type. This whole course, abstract data types. It's called a heap. Well, what does it look like, you might ask? Well, I'm going to say it's a binary tree progression. We just learned about binary trees, so we're going to move along. It's complete, filled top to bottom, left to right. Okay? So the first thing is it has to be complete, filled top to bottom, left to right. I hope you can read my handwriting. I always think it's pretty sloppy. And then I grade a paper test from a student. I'm like, yeah, no, I'm not so bad. But I get excited and I rush sometimes, and my handwriting is a little better than that. Yeah, thanks, Shay. Uh-huh. And then I think, should I type it up? Nah. Because when I have it typed up, it ends up looking like this. And you all don't want to see it like that. No. No type. No type. Okay. Second thing, not only is it complete, but every node is greater than or equal to its child. So it's complete, and every node is greater than or equal to its child. Three examples. The first one, I'm telling you, it is a heap. It is filled from top to bottom, left to right, and every parent is greater than its child. Now, I said this is a binary tree. It is not a binary search tree, because that when we did the lefts and the rights and the 8 would have been on the right, no left. Oh, that would have been a real mess. This is just a binary tree. It has to be complete, and the parent is greater than the child. Second one, I'm looking at it, and right away I'm saying not complete. There's nothing to the right of 8. The third one, rule number 2 is in effect. That's not right. The question comes, can this be fixed? And by the way I drew the arrows, I could actually fix this thing. And the way I fix it is a new term for today called percolate up. I'm going to be able to percolate up. Well, guess what? If there's a percolate up, guess what's going to go along with that? The old percolate down. And so we have a type of selection sort. I'm going to get a value and I'm going to move it from there. So now the next question is, okay, I worked with binary search trees and I used them as linked list, linked list, or an array. Well, we're not going to delve into the comparing them for time's sake, but I'm going to come out and say we're going to work with it as an array. So these values are going to be stored as an array. Okay. So, don't let them see that. Don't let them see that. I got excited and I filled that in. There we go. We're going to work with this as an array. So I need to go back to a quick thoughts about arrays. And if I remember the locations in the binary tree, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the array I'm working with is actually not going to have any blank space. It's just going to be filled. Now, I don't know what size to use to start.
Why would an array be more effective than a linked list?
And you remember when you were 8 years old and you asked a question of your parents and they said, because I said so?
Yeah, I didn't accept that as an answer.
No
I
kidding. No
yeah.
kidding. Yeah, no
Because that
kidding.
doesn't logically make sense.
Well,
Uh,
so once I show you how the heap works, you're going to see that the relocation of nodes would be crazy rearranging pointers the whole time.
okay.
For us, we only need to remember these two things. And these two things were where's the child at? And so we can swap array locations quicker than the prevs and nexts and all of that.
Okay, fair enough.
So I gave you kind of the because I said so answer with a little bit of explanation. Okay, so where are the children? In the corn. No, where are the children? Tutun, tutun. Well, if you looked really close, you could almost still see it. 2n plus 1, 2n plus 2. Two children. 2n plus 1, 2n plus 2. And the parent was at, here's 5. I want to get 2. Here's 6. I want to get 2.
Isn't it n mod 2?
About n minus 1 mod 2. Pretty close. You had the right idea. N mod 2 would give me 2 and 3. So I had to subtract one more off of that. All right. We're getting ready. We're getting ready. Okay. When it when it comes to a heap, it's a new data type. What do we have going on with this new data type? Well, I can construct an empty heap, which means I just have a pointer to that top node and it's null. If it's empty, that means that top pointer points to null. I have something called insert. And when I insert, I'm going to percolate up. I'm going to retrieve the largest. Retrieving the largest is what I did in my selection sort. I retrieved the value and tucked it away. So if you start thinking about what we're doing, and I have an array representation of this binary tree, and I'm retrieving the largest, where would I be moving the largest to? Well, in that one selection, we moved it to the end. And then the next one would be second from the end. Okay, so keep that in mind. Now, when I remove the largest, I'm going to follow it up with something called percolate down. Okay, where's the largest right now? If I built a heap by definition, where would the largest be?
the root.
Yes, be at the top. If I want to insert, where would I be inserting? Well, for this, we're going to be inserting at the end. We're going to do this thing called percolate up. Okay, so let's take a look at an example. Um, do 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 do. I have. We're gonna start out with. Let me get my camera right. Remove. Okay, we just talked about a removed. I don't know where it went in my notes. Where are my notes? Oh, there it is. Remove. Remove the largest. And along with remove the largest, I said percolate down. Down. All right, so the basics are going to look something like this. I'm going to have 77, 60, 41, 15, 55, and 35. And I'm going to stop right there. It's complete and it fits rule number 2. Every parent is greater than a child. If I looked at the array version, 77, 60, 41, 15, 55, and 35. Now, I said what we're going to do here is remove the largest, but I don't want to throw it away. So where would the largest need to go? Well, the largest is in the first spot. Where would the largest go?
The end.
To the end, right? To the end. So now I'm going to switch 77 and 35. So in the world of my arrays, I am switching 77 and 35. Okay. What's that look like here? Well, now I have 35, 60, 41, 15, 55, and 77. Cool. Do I have a heap? No. What did I say? I'm going to remove the largest and percolate down. So percolate down means this 35 is going to get percolated down. Excuse me. Which side should I percolate it down? Should I switch with what? This 35 is going to come down. Which one should it go down to, the 60 or the 41?
60.
Why?
Because if you switch it with 41, then 41 is still going to be smaller than 60.
Yeah, yeah. So I'm going to bring the 60 up and go 35 because I'm turning this back into a heap. Is it a heap?
Nope.
Nope. So I had to switch these two, and now I'm going to go one more time and switch these two. Now I have 60, 55, 41, 15, 35, and 77. Is it a heap?
Yes.
Yes. Yep, it is a heap. Don't consider 77. We've eliminated a little, it's easy for me to say, eliminated that, locked it in at the end, and said, hammer time. Don't touch that. Oh, hammer time. Okay. Do it again. What am I going to switch? The 60 and the 35. So now I have 35. 35 likes to be at the top. 55, 15, 41, 60 is now locked in place. 77 is now locked in place. Now that I did the swap, I'm gonna heapify. Heapify. Looks like all I have to switch is 35, excuse me, 55 and 35. 15 stays there. Here's 41. Here is 60. And here is 77. I have a heap. So now I swap. Then I heapify. Then I'll have a heap. And you can see 55 and 15 are going to get exchanged now. And it's just going to keep going. 15, 35, 41, 55, 60, and 77. Okay. Are you getting the concept of how this works?
So once something's been moved, it just never gets touched again.
Yeah, these guys never get touched again because they're in sorted order. It's just like those arrays from earlier. If I started at 0 and went to the rest, 0 spot was then done. So then I moved to 1 and compared it with the rest. Then 1 was done. So it's the same thing here. These at the end are slowly getting done, and I'm only working with values in the front.
Got it.
Woo! Percolate down. Percolate down. I remove the largest, and I'm going to end up with my sort. That would be how the sort works. Nice. Check. Remove the largest. This is like delete and insert. Questions on percolate down. Removing the largest.
So did we just order it to like where was the deletion for? Because we would delete 77, right?
Well, these guys are here stored, but after you do that, now we're changing our size to work with this much. And once that value got stored, which was 60, then we were only working with this group of numbers. So we kept the original idea of an array. Wow, that's just bad. I'm trying to look at the camera and do it. And then we worked with one less, and then we would work with one, and we just keep working with a smaller and smaller list.
Okay, I see.
So that's where the n comes in for my big O notation, because I'm going through all the values. But then it kicks in with that log n. Again, I apologize. I'm looking at my screen while I write sometimes, and it just doesn't go so good. Bam. Any other questions?
Yeah. If we're doing a min heap, because this is a max heap, because we're pulling the max value out. If we're doing a min heap, would we just reverse it to where we're always getting the smallest value?
That's the
Okay.
whole switching the less than and greater thans from ascending to descending.
Got it.
Yep. Yep. And this, of course, is giving me ascending. All right. I'm going to try to write a little nicer this time. Probably not. Insert an item. Way number 1. Way number 1. Okay. I'm going to take this list of numbers 60, 55, 41, 15, 35, 50, 58. Right now I have an empty heap and I want to start inserting those numbers. So the first rule is we're going to do this. Add ADD to the end and percolate up. Again, we're working on concepts here. When you get down into the nitty gritty and start working with the code, you have all that 2n plus 1 and 2n plus 2 and that n minus 1 mod or integer division 2 to help you move around. but we need to just figure out how we're moving around first. Fortunately, we don't have to delve into the code again. It's a time limit. If we had a full year instead of a semester, it would be different. But probably y'all could get it on your own. Okay, add to the end and percolate up. First number 60. Well, that's going to be up there at the top. Nothing really exciting happens. Nothing really exciting happens. 55. Do I need to percolate up? No, we're still good. We're complete, and the parent is greater than the child. 41. Oh, this is nice. Just moving right along.
Could you explain what you mean by percolating up again?
Yep, you're going to see it in a couple seconds. Okay. 15. So far, all the children are smaller. But if I added another number, and we can do that right now if you all want. After 15, we're going to add 80. So I messed up our list. We're putting in 80. So my next location is here, and I go, uh-oh, this is no longer a heap. I need to percolate up. Well, when I percolate up, 55 goes here, 80 goes there. Uh-oh, I'm still percolating up. 80 now goes here, and 60 goes here. So it started at the bottom, and if the parent was smaller, we swapped. Start at the end, percolate up would be if the parent is smaller, swap them. Okay. It's not too bad. I need a clean one. Here's 80. Here's 60, 41, 15, 55. Next number I'm adding is 35. Still a heap. Next number I'm adding is 50. Still a heap. This is very good test data. Next number is 58. Uh-oh, there
50
goes.
is less than 41.
Yes, it is. Those two should have been swapped. My bad. And then as we said it before, I messed up. These two should be swapped as well. So now every parent is greater than a child. So this percolating up, again, I'm going to be checking n-1 integer division 2. And if I need to swap them, I swap them. Oh, that makes kind of sense. So if I'm looking at the array, I just jump to n-1 mod 2 location and see if they need swapped. And then I check it with n-1 integer division 2 location, and so forth and so forth. That doesn't seem too bad, does it? That doesn't seem too bad.
I just had a quick question.
Yep.
Why is 41 going to the right initially?
Because I'm filling in left to right.
Okay.
I put numbers in. I put in 60, then I went next row, left to right, left, and I just keep filling in left to right. And as I fill in, it stays complete, and then the percolate up will make it a heap. And then I can use that heap sort, take the top off and swap them and percolate down and on and on and on.
So you're filling in the data and then sorting after, essentially?
Percolating up, and then
Mhm.
once it's a heap and I'm all done with data, then I can stop.
Okay, I got you. I got you. Thank you.
Yeah. Okay. The second method to insert an item. So as I inserted, I percolated up. Okay. As I inserted, I percolated up. And insert one, perk up. How many percolations could I have possibly done? All but the first one, right? I could have had to percolate here and percolate here. I'd have to do a lot of percolations. I'd be doing n minus one percolations. Worst case scenario. Okay, so here's a second way to do it. I'm just going to take all the numbers and make a tree. So I'm going to start out by just making a tree. Oh, 60 and 55, 41. I'm just filling the array with data.
Wait, I have a question.
Yeah.
Wouldn't you technically end up potentially percolating up more than that? Like, for example, if you had, I don't know, 80 at the very bottom of the tree, and then you had to percolate up multiple times to get it to be in the correct order.
Yes, you're absolutely correct. That would be n minus one times I could swap once, twice, three times. Yeah, we could mess around with the number of rows and so on and so on. This was where the parent was. Yeah. But I'm just saying a complete percolate up. I mean, I have to check to see if I percolate up.
Right.
But yeah. You're absolutely right. So we could be doing a lot of swapping potentially. Yeah, we'd have to do numbers and because these two would both potentially be one. These would all be potentially two. These would all be potentially three. And then
Yeah, so it's an exponential times a
yeah.
yeah.
Yep. That's a good question. Never had that question before. Right. So my other scenario is first thing I'm going to do is make a tree. Basically, all I'm doing is fill the array. So now the way I'm going to do this one is I'm going to start at the first node that is not a leaf. Start at, I want to say lowest node that is not a leaf. Where would that be?
15.
15.
15, right? 15 is going to be the first one. Now, what am I going to do? Tell me what you think should probably happen here. I only know two things, right?
Percolate down.
Yep. Start at the lowest node that is not a leaf, then perk down. I'd have to figure out what that is. And I see the picture, draw the picture. I see the picture and I can get there. I'd have to look at some cases to figure out how I can find out what it is. All right, so I'm going to percolate down starting at 15. There goes 15. There goes 58. The next one I'm going to take a look at is 41. Percolate down. 50. 41. The next one I'm going to look at is 55. Yep. Percolate down. 55, 80. The last one I'm going to look at is 60. I'm going to percolate down. Now, is it possible that I'd have to percolate all the way down? Yeah, if this number was one, I'd have to be going all the way down. It's not. Could have come up with better test data, but that now becomes the 80 and that becomes the 60. And lo and behold, I got to 60 and I'm like, bigger and bigger. I could stop. Lo and behold, I had a lot less percolating going on. But two ways to insert items to make myself a heap. Ta-da!
So with this, you're just comparing if it's greater than or less than both its children, and then making a swap based on that.
And then keep going if I can. Keep going if I can. Can we do another one of that? Yes, we're doing another insert. List of numbers. 1, 15, 30, 8, 100, 16, and 2.
Can we add a duplicate number in this example?
We can. Let's add 30. So the first method was insert or add at the end. And perk up. Second method was fill, then perk down. I'm going to give you a minute. I'm going to pause. Add to the end and percolate up. I have a 1. I have a 15. Yep, I percolated up. I have 30. Yep, I percolated up. 1 stays, 15 goes down. I added 8, 30, 8, 1, 15. I have 100. Still filling in by way of that left side. It's going to switch with the 8 and then switch with the 30. So here's the 100. The 30 ended up there. The 8 ended up over here. $16. 16 and 15. 2. All right, so I have 100. I have 30. I have 16. 1, 8, 15, and 2. Just wanted to make sure I wrote it correctly and everything looks good. I added the 16. Now I'm going to add 30. So if I did the percolate up, I have 100. There's 30. There's 16. There's 30. There's 8, 15, 2, and 1. So by doing this, I think it answers Andrea's question of duplicates. I only need to swap if the one above or if the one I'm looking at is greater than, or this one is less than. I don't need to bring in the equals part of it. Add at the end and percolate up. Okay. Number 2. Fill the array or fill the binary tree. Well, it is an array. I have 1, 15, 30, 8, 100, 16, 2, and 30. Again, practicing these, it ends up being pretty easy after a minimal number of practices. But the first thing I have to do is identify where to start. And it would be the first node. It would be the first, if this was a linked list, it would be the first node that has a value that it's pointing to and a null. These are two nulls, two nulls, two nulls, two nulls. Uh-oh. First one, it has a value. If it was an array, oh, I'd have to look at, yeah, something. Now, where do I start?
The 8.
The 8. Very good. And I percolate down. 1 doesn't change, 15 doesn't change, 30 doesn't change. This does. It becomes a 30, that becomes an 8, that stays 100, that stays 16, and that stays 2. Okay, so I percolated down. That's going to be one of the hard things when you relook at this in 6 or 7 days. Okay, when I percolate down, I keep going down. When I percolated up, I kept going up. So I looked at the 8. The next number to look at is 30, and I percolate down. So 1 stays, 15 stays. This is going to not move. That's not going to move. This is 30. This is 100. This is 16. This is 2. And this is 8. So I'm keeping track. I started here. I went to there. Now I'm going to the 15. Looks like I'm going to percolate down and switch it with the 100. 1, 100, 30, 30. Here's where the 15 went, and here's the 8. And whoops. It had the 15 swapped with the 100, and it had no other place to go. So it sits here. And as I'm looking at it, as I'm drawing, I'm starting to see, yeah, there's a mini heap. There's a mini heap. These are all starting to work out pretty good. The final number is the 1. It gets switched with the 100. It gets switched with the 30. And it's going to work its way all the way down. So the 100 is going to be here. Temporarily, the 1 goes there. And then the 1's going to here. And then the 1's going to there. So 100, 30, 30, 8, 15, 16, 2, and I have my heap.
Question.
Yep.
Why can't we start at the root on like this second example? Why can't we start at the root and percolate it all the way down and then start back at the top?
If I start here, oh, you want to start up there,
Yes, sir.
and percolate down.
Yeah,
So let's think about it. My guess of an answer is you're going to be doing some percolating that you hit a spot where you need to be done. So let's look. 1 would go down to here, and 15 would be up there, and 100 would be up there. So I've already done this spot, and now I would be moving to 100. And if I'm percolating down, would the 100 ever make it up to the top spot?
Okay. No.
Yep. Just walking through and answered your question that quick. Cool. That's a pretty good question.
So the two methods produced different trees. Slightly, but
Lately, but both of them are, by definition, a heap.
right.
And now I can heap sort. I can do the heap sort. Yep. Questions? All right. I don't have anything for the last few minutes of class. Wouldn't make much sense to get into groups. So we're going to knock it off there. It's a long one.